We'll continue with the liver, liver and gallbladder. These are accessory organs to the alimentary canal. The liver is a very, very, very important organ. It's included in the digestive system, but it has functions far outside of the digestive system. It's the largest gland in the body, and it's divided into 4 lobes. When I was a student, we considered it 3 lobes, right, left, and caudate. But there was a little bump on the caudate lobe, which has now been identified as a 4th lobe called the quadrate lobe, and so which means left, right, tail, and 4th lobe. It sits on the right side, right below the diaphragm. It's by far the largest organ in the body. There's a ligament that suspends it called the falciform ligament, then it separates the right and left lobes from each other. The falciform ligament goes onto the diaphragm and right around to the anterior abdominal wall. There's another ligament called the ligamentum teres, which means the round ligament, and it goes to the liver from the back of your umbilicus, from your belly button. And it used to be the vein and artery, but really the vein, that went out to the placenta through the umbilical cord. Once the umbilical cord is cut, then this degenerates, and the connective tissue, that's all that's left, so it's called the round ligament. It looks like this. The underside of it looks like this. This staining here on this specimen is really from the vena cava, so a lot of that is an artifact of them putting blue latex in the vena cava, and there tends to be the gallbladder right here, so that can show like a green stain from bile. So the gallbladder is right here. So oftentimes you'll see specimens that are stained green from there. Again, this quadrate lobe didn't used to be considered a separate lobe, but because of where the ligamentum teres goes in, they've decided just recently, like literally in the last 10 years, to start calling it a 4th lobe. The lesser omentum anchors it to the stomach. There's a hepatic artery and vein that go in there. There are a couple of bile ducts. There are bile ducts from each lobe, and so there's a hepatic duct from each lobe, and then there's the common hepatic duct that leaves the liver. The cystic duct connects it to the gallbladder, and the bile duct is the common hepatic duct and the cystic duct together. I did that on the last video. But again, same picture, it looks like this. So the hepatic ducts come here to the common hepatic duct. The cystic duct goes to and from the gallbladder. The union of that is the common bile duct, which unites with the pancreatic duct at the hepatopancreatic ampulla and the hepatopancreatic sphincter going into the duodenum. So the liver is made up of a number of repeating lobules. They're exactly the same. So these are the functional units. Um, this is where the work of the liver happens. On my board exams many years ago, the physiology exam was 5 questions long, and one of the questions was identify and discuss 10 major functions of the liver. I could only come up with 9 of them at the time. I could probably come up with about 12 now. Not all of them have to do with the digestive system. This is the place where gluconeogenesis happens. This is the place where glycogen gets stored. This is the place where drugs are detoxified, where alcohol is detoxified, various things like that. But we'll talk about the structure of it, the microscopic structure of it. The cells that do the functions are called hepatocytes, and they are found as plates all surrounding a central vein. Blood is brought to these little hexagonal structures, these lobules, and it flows past the hepatocytes, where things leave that blood, go into the hepatocytes, things leave the hepatocytes and go back into the blood. And then, generally speaking, that changed blood flows out this central vein. So it looks like this. It's kind of a honeycomb. They're little hexagons. And in 3 of the corners, there's something called the triad. And it's a hepatic portal vein. It is an artery, and there is a bile duct. And at each place that happens, each triad services 3 lobules. So each lobule is serviced by 3 triads that are doing 2 other lobules. So basically this works as a unit where these 2, and these 2 are all served by the same triads, same 3 triads that are doing this one. The central hole is the central vein. So at each triad, like I say, there's a bile duct that receives bile that's made by the liver, and there's blood delivered by both the portal arteriole and the hepatic portal venule, part of the portal vein. And then there are sinusoids. They're kind of like capillaries, but they're leakier. And there's macrophages that live in there as well. So it looks like this. Blood is delivered to the liver lobule, here from the hepatic portal vein, here from the hepatic artery, right? And the blood flows through these sinusoids all around in here. And you'll notice that each hepatocyte borders its waterfront property onto one of these sinusoids. Things go vertically as well as towards the center. The blood that flows in here is nutrient rich. The blood that flows in here is oxygen rich. The 2 sources of blood merge, so you have nutrient rich, oxygen rich blood here that will give off its oxygen, give off all the nutrients into the hepatocytes, where it gets processed and dealt with. This might be alcohol rich, in which case the alcohol will go in here and be detoxified by, it might be drug rich, in which case the drugs go in here and they'll get detoxified. Whatever is going on is here. The liver also is releasing things like glucose at times of need, both from glycogenolysis and gluconeogenesis. And so the blood that flows into here varies depending on the body's needs. Now, behind all of these, there's kind of a back alley behind all of these hepatocytes. And this is, the hepatocytes make bile. And all this bile flows through these little canals called canaliculi, and they eventually flow into this bile duct. And then the bile duct carries the bile down, and they come together and come together and come together until they form the hepatic ducts of the bilious system. So what's going on in all these hepatocytes? Nutrients are processed, vitamins are stored, detoxification happens, and bile is produced at the tune of about almost 1 liter a day. Now, bile is a very, very alkaline solution, and it's yellow-green because there's two things that it does. One, it gets rid of the pigments from old worn-out blood cells, really the heme from the hemoglobin, with the iron removed, because the liver stores the iron. What's left over is something we can't use, so we excrete it. It's called bilirubin. It's what makes the bile very yellow. Anybody who's ever had dry heaves and has puked up that bright yellow, that kind of chrome yellow, very bitter tasting stuff, that's bile. So, and the color is a waste product. It ends up never being broken down or reabsorbed. It just oxidizes, and it's what makes our poop brown. No matter what color of food you're eating, your poop tends to be brown. And that's from the bilirubin. They're old red blood cells. The pigment, anyways. Also in there is something called bile salts. It's cholesterol, which is a fat-soluble, well, it's a type of fat. And so it mixes with the fat and causes fat to emulsify and become absorbable. If you put fat and water together, it's going to clump up, just like salad dressing separates. Emulsifying it means that you are mixing it together. You have little tiny droplets of the fat mixed in the water soluble stuff. It's like shaking the salad dressing. That really is emulsifying it. Now, there's some cholesterol and there's some neutral fats. There's phospholipids in there. You notice they're all the different types of fats. And there's various electrolytes. The thing about the electrolytes is that they are polar, where the cholesterol, neutral fats, and phospholipids are not. Well, the phospholipids are polar. They have a polar and a non-polar end. But basically what this is all about is to facilitate the absorption of dietary fat. It doesn't cause any digestion. There's no enzymes in here. All it does is emulsify, gives more surface area for the lipases, the digestive enzymes, to break it down. So what ends up happening then is the products of this, the cholesterol and all of the products of the bile salts, end up getting reabsorbed at the ileum, where they go in the hepatic portal vein, and they go back to the liver, and then they're back secreted in the bile. So it's a constant recycling of this. The only thing that ends up being gotten rid of, excreted, is the bilirubin, the bile red. Now, the gallbladder is situated right along this path because there's no sense in dripping bile into the duodenum when there's no fatty foods. So what we do is we store the bile that's being made at a constant rate in this squeeze ball called the gallbladder, the cholecyst, the bile bag, as it were. And what the gallbladder does is it reabsorbs water out of the bile and makes it more concentrated, makes it more powerful. When there's the presence of fat in the duodenum, then the enteroenteric cells release a hormone called cholecystokinin, which causes the gallbladder to squeeze and squirts this concentrated bile out in to mix with the fats in the duodenum, and thus emulsifying them, making them more digestible. This is a good thing, but it's not a necessary thing. So that's why people can live quite well without their gallbladder, because they still are producing bile. They just won't absorb dietary fats as well. Their poop tends to stink more and float more because of the amount of fat that's in it. But that's neither here nor there. We don't tend to be short of fat in our diets.